So now we know that terrestrial biomes are distributed with latitude, but we don't really find very clear bands right across the world. They don't form like a perfect horizontal stripe of tropical rainforest or a perfect horizontal stripe of desert. And there are a number of other factors that are going to shape these terrestrial biomes. And we're going to talk about something like microclimate, which is how you can get quite drastic changes in temperature and precipitation by going over a very short distance. And so if you're looking at a mountain, as you go up the mountain, you're going to get cooler weather. Depending on what side of the mountain, you can have rainy sides, shady sides, cooler sides, hotter sides, and you can have different soils at different spots. So these are all going to affect what what types of vegetation you find in different places. So this is section 2.2 in your textbook, other factors that shape terrestrial biomes. So this concept of microclimate is something we're going to be talking about a lot when we're talking about temperature and water relations. Microclimate, the climate right around where the organism is living, is important and is going to influence what can actually live there. Obviously, if you are in a shady spot or a sunny spot, that's going to be a very different microclimate. The presence of mountains influences temperature. As you go up in elevation, it gets much cooler, the air is thinner. Mountains also exhibit something called a rain shadow effect. A rain shadow, one side of the mountain is going to have a prevailing wind, something like these trade winds we've been talking about, that might be bringing moisture off an ocean or moisture off a lake. As the air is moving up the side of the mountain, it's going to cool and condense, and it's all going to rain on the rainy side of the mountain. And that means the leeward side, the side that's sheltered more from that wind, has dry air. It's already dumped all its rain on one side. So that lee side of the mountain is a rain shadow. So there's more moisture on the windward side and a drier climate on the leeward side. This is a nice figure from your textbook. So here we have shown we've got evaporation of water coming up off of the ocean, or this could even be one of the Great Lakes. We've got this prevailing wind. So this might be the Pacific Ocean. The wind is coming off the Pacific Ocean. It's carrying all this moisture that's being pushed up the mountains. So as it's going up the mountains, it's going to start to cool. When it cools, it's going to form the clouds, and then the clouds are going to start raining on that side of the mountain. So then we get the rainfall occurring on the rainy side. By the time it's gone over the mountain now, it's all cooled off. When it's cooled off, the air condenses. As the air condenses, it's the dry air will then fall down the other side, and that's the rain shadow. There's the rain shadow. There's no rain in a rain shadow. So because of microclimate, when you have a lot of variation in elevation, you can find variation in the different types of vegetation that you get growing in different areas. And so this is the figure out of your textbook where you're showing the biomes in the western United States, and the biome map becomes quite complicated. So we can see that the yellow areas, which is the desert areas, we've got the Sierra Nevada mountains here, and to the right of the Sierra Nevada mountains, we've got all this desert area, and this desert area has a little bit of woodland and little bits of forest, depending on little outcroppings here and there. But for the most part, this whole area is a desert, and we've got these big mountains that are forcing the air up and over. We've got the Cascade Mountains, we've got the Sierra Nevada Mountains, and you've got a lot of rainfall on the ocean side. So over here we have the Pacific Ocean. We have lots of rainfall as the air is forced up over those mountains, and then it's all dry. So when you go past those mountains and the air continues to blow in this direction, so you've got the westerly trade winds, you really have run out of moisture and you end up with a desert biome. When we look at the climagraphs for the US, then you can see that if we just look at average precipitation and average temperature, this is sort of like the figure we saw before. We've got the temperature going up the y-axis here, and we've got the precipitation going across the x-axis, which is a little different than what we had seen before. But we can see a lot of overlap then in these biomes, and this can be in part due to effects of having the same temperatures, the same precipitation, but you're changing, in some cases, elevation. You could be on the rain shadow of something, or it could be also differences in soil type. Just a quick introduction to soil. You can take entire courses in soil, and learn about all the different types of soils and the different layers in the soil. So this is just a very simple overview, and we're looking at soil being a mixture of the minerals. We've got the non-living materials. We've got the sand, the silt, the clay, the gravel, the stones in the soil. But we also have living things in the soil. We have organic material. We've got worms. We've got insect larvae. We've got moles. So it's a mixture of living and non-living material making up the soil. Soil is not sterile. It's full of bacteria, full of fungus, full of living organisms. The classification of soil is based on the vertical layers, which are called soil horizons. When you're talking about a vertical layer, we mean as we go down vertically, you find different soil types, but they are all parallel to the soil horizon. So as we go down from the surface, down deeper, we find changes in the soil, and those are your soil horizons. So when you look at a soil, you dig down in a soil's always changing. Animals are moving it around. The rainfall is going to be different at different times of the year. You're seeing a snapshot of what that soil looks like at that time. The different layers, the thickness of the layers, whether a layer even exists or not, is going to depend on the climate and the underlying rock material, the geology in an area. You might have an organic layer on the top, which is just all your leaves that have fallen, dead organisms. So this is just the most superficial, the top layer of your soil. When things start to decompose, that gets mixed in with the sand, the silt, the clay, the gravel, and you get what is called a horizon. As it rains, it's going to wash nutrients from that A horizon down deeper into the soil. And you're going to find the smaller particles like clay being moved down from the A horizon into the B horizon. Because so many nutrients move down here and the water moves down here, plants like to get their roots down there. It's a much more stable condition for getting nutrients and roots and water. And then you get deep enough, especially if you're living in New Jersey, you start digging even deeper, you're probably going to find some sand, or depending on where you live, you might find gravel, bits of rock. This is the underlying geology, the underlying parent material that the soil was built from. So here's a typical soil profile. We can see the organic horizon on the top where we have all the litter material. Beneath that, we can see that we are getting material leached into that, and it starts to mix in. We get material deposited down in this B horizon, and you can see these trees are getting their roots down there. There's lots of water, there's less evaporation, and lots of nutrients down there. And then down here in the C horizon, we can see whatever this underlying bedrock is breaking apart, it's weathering, and it's being incorporated into the soil. So that's where your minerals are coming from. If you flip back in your chapter, or if you're online, you go to the applications section of your chapter, which is right at the very end. It's after section 2.3, but it's before the summary and review questions. There's an application called Finer Climatic Variation over Time and Space, and it is talking a little bit more about microclimate and talking about temporal changes as well. So we get very fine scale changes in the weather and in the climate, and they introduced the concept of the Palmer Drought Severity Index, which is used to characterize climatic variation. And it's been historically used by farmers to indicate drought conditions. It will also tell you about wet conditions. And a drought is defined as an extended period of dry weather where the precipitation has been reduced sufficiently that it's going to damage the crops. And so that can help, that can sort of hurt the ecosystems. It can also cause water shortages for people. And right now, we have had so many years of drought in the American Southwest that it has been categorized as a mega drought because it's been so many years of drought. So climate diagrams, remember we're looking at average temperature, average precipitation. So that's long-term averages or a long period of time. But often we can find these variations that show that things can be for a period of time quite different from average. And we'll find later when we're talking about some, well, we'll use an example of Galapagos finches, where there's certain years where they had more rainfall and less rainfall, and how that impacts their populations. So some regions are climatically more stable, and other regions are climatically more variable than others. And regions that are under the influence of the El Nino Southern Oscillation, which is the shifting of the ocean patterns so that the ocean currents are instead of going away from South America west across the Pacific, shift go east across the Pacific. When we get an El Nino, that's going to change your precipitation and your temperature patterns in areas that are affected by that very significantly. The example they show in your textbook is looking at the Palmer Drought Index, which is how we measure, one way of measuring drought severity. And this is from the NOAA data. And this is showing you that some areas can experience significant droughts. And so we know about the droughts in California causing a lot of fires. When you have an extreme drought, you obviously are going to have increased fire risks. Other areas, though, at the same time could be having more moisture falling than expected. Excuse me. So we can also see over the years and over time, we can see across the bottom of this graph, we can find not only do we find changes from state to state and county to county across the country, but over time, when you're looking at a particular area, and this is looking, I believe, at the area around Manhattan, Kansas, we can see that some periods of time you get years where you have drought, and then we have periods of years where we have additional rainfall. So one single location can get one or the other. Now, we like to think of the biomes as being something stable, something that's always the same, but we know that they do change. Species come and go, things happen. We see this now with climate change. We're seeing a lot of changes in a lot of the biomes. This is an example of the national tree of Costa Rica. This is the monkey ear tree or the elephant ear tree. It's a nice big shade tree, and they were finding that they were having difficulty keeping this tree going, that the seeds were not germinating from this tree. When they looked at the natural history of this tree and the seeds and what was happening is that normally the tree will drop its seeds down onto the ground and it's too shady right under the tree. And so in the past they were eaten by seed dispersers. So the seeds were eaten by something that was somewhat like a camel that lived in that area thousands of years ago, and they would then eat the seeds that had fallen under the tree, and when they walked away, they could, in their feces, disperse the seeds onto the ground in a pile of nice, healthy, fertile manure, and then the next tree could grow up in that spot. Once they understood that natural history, then in the national park in Costa Rica, they were able to reintroduce, or not reintroduce, but introduce domestic seed dispersers. So they could take domesticated horses and cattle, and they could eat the seeds. So you can see them eating the seeds here. And then when they wandered around, they could defecate, and the little seedlings would be in the dung and able to grow. So we know that understanding the natural history helps us understand how these biomes work. And this is where natural history is key to understanding a lot of how to help and protect the biomes. So here we used it to solve a particular problem.